Maybe this will work. Yeah. All right. Okay. So I'll through the course of the semester, I'll probably get to know each of you guys. I'm not going to have you guys introduce yourselves to me, but so I'm Ken Yamamoto. I know I didn't say this in the past, but you guys can call me Ken. You don't have to call me Professor or Dr. Yamamoto. You just call me Ken. So I um, am originally from New York City. I was born in Queens, New York City, and then I moved to Atlanta, Georgia, kind of in middle school, and then I ended up going to the University of Georgia for college, uh, and majored in math and chemistry. And I went to graduate school in University of Arizona in Tucson, Arizona, and got my PhD in applied mathematics and then came here. So I defended during the pandemic and moved in the middle of the pandemic. So I've been here for a few years. And over the winter break, I went home in Georgia where my parents and my brother live, and we hung out and ate good food and watched movies and things. I love playing the piano, so I played some piano when I was at home. And I try to play when I'm here as well. I speak Japanese. I speak English, of course, and I also lived in Germany during high school, so I speak some German. Yeah, so that's kind of me. Let me just close this. All right, so I'm gonna jump right into describing sort of the layout of the class. This is like the Canvas page. What you'll see when you first get into our Canvas page, at least what I see on my end. And there's a bunch of links up here that are going to be useful, but I'm gonna first jump into the simple syllabus and just go through some highlights. Um, uh, yeah, so let's see. These office hours are not the correct. Let me just fix those. I'm gonna say this is still to be determined. Because I want to send out an email to everyone that will give you a poll for you to decide when you want to have the office hours. So I'll send an email out. I don't know if it's going to update, but I'll send an email out. We'll choose a time that works for most people. This is the textbook. It's got a link here that lets you access it online. If you have your SMU login, then you'll be able to go in that. We'll do that later. The grading, it's basically homework and tests. So the homework, there's going to be one every week. And then there's also something called daily practices, which I'll give one every class period. You'll get one for every single class period. And the daily practice is optional and it's for bonus credit towards your homework grade. And so, if you don't get a perfect homework grade, you can kind of do the daily practices and get a good grade from that. Then there's the class exams. There's three midterm exams that are all equally weighted, and then there's one final exam. So the in-class exams are 100 points each. So there's three of them, 300 points. The final exam is worth double the single midterms. And then if you let's see, is it gonna see, I'm gonna jump to, let's see if I can show. So if you have, if we go back, if I show me, let's see where here. I want to show the breakdown. Let's see the course policy. This is just the Google Doc version of the course policy, and I can't find it on my simple syllabus. So this right here says that the 3 exams, in-class exams are 300 points, final exams 200 points. The homework is 125 points, so there's 365 points in the course. And if you actually did the percentage, the homework is worth 20% of your grade, and then the tests end up being worth 80% of your grade. So there's also a little word on attendance. I don't take strict attendance, but I kind of have a good idea who's coming. And it's a slight it's not like a formal thing in the grade scheme, but like if you end up being really close to the border of the next higher grade, if you know, been coming to class and you've been participating, then it becomes a consideration that I might bump you up. But it's not like a formal part of your grade, so it doesn't hurt you, but it could help you at the end if you end up being very close to the border. This is apparently the final exam the time that we have for our final exam, which is posted by the university. And then I don't think there's anything else that I wanted to say besides that. Let's see. This is just the general calendar, but I think that's basically the main idea. Let's go into the each of these links right here. So if you click on the class calendar, the calendar in the syllabus, the simple syllabus is our general working plan, but this is going to give you exactly what we're going to cover on each day. So this is today right here. And I update this regularly throughout the class. I don't really touch the simple syllabus after I've already posted it. And so this is sort of the place you want to go for what we're going to cover each day. And then I do have like, so DP means daily practice and HW means homework. And these are basically due at the end of those days. So it's at like 11:59 at those days is what it's set to be due. And then this is just a copy if you wanted to look ahead of like what we're going to be doing. And this banner of links is everywhere. So it's like in the Canvas page. It's also here. It's going to be almost in every single document you see. The written homework list. So this is just going to jump right into like, so they're just from the textbook. So you can click on the online textbook here. It's also right here too. So they're all the same. And if you're signed in, it'll give you access through the university. And you can just click on, you can download each chapter. I think you can even open it on your browser and look through. And the homework problems are from each section in the textbook. So section 1.2 and 1.3, that symbol means section. And we actually have a grader in our class because you guys, it's a big enough class for me to get one. But because the grader only has a limited amount of time that they can work per week, it's going to be too much to have them grade every single problem. So only the problems that are in the red font are going to be the ones that the grader will grade. And the black ones won't be graded, but you should do them. I post solutions fully worked out for every single problem. So not just the red problems, but also the black problems. You just don't know if you're getting the black problems right or wrong unless you look at my solutions and compare, your work with my solutions. So there's a little bit of work on your end to make sure that you are getting all the problems correct. But you're going to get direct feedback on just the red problems. Yes. They're after the due date. Yeah. So everything is not just by completion, it's by also making sure that by accuracy. So I will have the grader not just check that you did it. You want feedback, right? Because otherwise, it'd just be like you did it, check, but you don't know if you're getting it right or wrong. So you want to get feedback on whether you're getting it right or wrong. And you want if you get a lower homework grade, you want that to, maybe be a wake-up call. Oh yeah, I'm actually not understanding it. So it'll be like close, at least a prediction of how you're doing, like, and how you might expect to do on a test later. Same with the daily practices. So if you go under, I don't know, if you click on this right here, I guess there's one right here. So then you click on this, it will jump to that daily practice, which is actually part of a large Google Doc. So just so it's gonna jump to essentially it's gonna jump here. And it's just a short set of like 3 problems. Sometimes it's just 2 problems, sometimes it's just 1 problem. And you just do those, and then for all of the homeworks and the daily practices, it does say right here to submit a single PDF file. And so don't have like separate files for like each individual problem, just put it into one single file and then put it in order. That's mostly for the grader to be able to tell like that, they're not just scrolling around looking for your problems. So if you put them in order, and otherwise, points might get deducted. And so that's what you do. You just take these, you just write it on a separate piece of paper, you photo scan it and upload it on Canvas as a PDF. And the same with the homework. The homework, of course, is just these problems. Okay. So a note that I will say, so this is something that I experienced in the past. So of course the ones that are actually graded are these red problems. The black problems are not graded. Also, the daily practices are, I mean, they will be graded, but they're bonus credit. So you might think I could just do the red problems and be fine. In the past, most of the time, if you just do the red problems, you may like not quite even get a C in the class. You want to do all the problems, including the black problems. That'll maybe allow you to, get like a C or a B in the class. And then the people who usually get an A in the class not only do all the problems, including the black ones here, but also do the daily practices. And it's not like guaranteed that you'll get an A if you did all of that, but generally like it's like a good correlation. It's because of the amount of practice you're getting. You need to get that extra good enough practice to do it. And I wanted to emphasize that like even though it's like bonus or optional, it's really you should be doing them all if you want to get a good grade in the class. And it's just me trying to be a little bit more lenient with you guys. The very first time I taught differential equations, all of it was required. So I graded every single problem in the homework, and I also graded every single daily practice, and the daily practices were also for a grade. They weren't like bonus. So everybody felt compelled to do it. And then that was the semester I ended up, having almost everybody get A's in the class. So, and then after I started to be more lenient and say, okay, now you can have these as bonus and stuff, people start to not do them. And then it's usually going to result in not enough practice. So try to really do those and think of them as required, even though points wise, it's not as strict. Okay, so let's jump to the other links here. So that's the written homework list. The course policy is like what we just saw, which is this thing right here. It's just the Google Doc version. The online textbook. Okay, so I like to use this virtual board. And basically I have a blank PDF of problems that are already typed in, and then I write on top of it. And you can always get access to this by clicking on this blank lecture PDF. So if you wanted to see what I'm going to be writing on during class ahead of time, some people might have a tablet and you might want to download this and then like import it into one of your note-taking apps, and then you can just write on it as I'm writing on it. This is what's available there. The blank lecture, that's just the Google Doc so it's just going to give you, it's just going to open this thing right here. And then the filled out lectures is going to be whatever I wrote in class, I upload it. So it's going to be like PDF of this, but with all my writing on top of it. And so that'll always be there. And then the other thing that's important is the office hours / appointments. So if you click on this, then you can see these two links right here. So if you click on one of those amounts of times, then you can schedule. So you can say, oh, I want to, meet with him like on Monday next week or something. And then you type your name and your email. And these are optional. If you want it to be Zoom, then you can just say yes here. If you want it to be private, then you can say private here. Private should be only for grades. If you wanted to have one-on-one math help, that's also, I can do that, but you want to type preferred for one-on-one help. That's just so I'm aware that like, oh, you want to meet with me one-on-one, but if I'm extremely busy that week, then other people might join in. So, I don't, think it's a big deal if you have a question on something and there's like two other people or one other person joining us at the same time. So what happens is that when you actually book a time, that time slot doesn't necessarily go away for other people to book. And so if somebody else ends up wanting to take that time, they can still take it. If you say private, then I'll take it off from the selection. So another person can't select that time anymore. If you said preferred and I'm not too busy, then I'll probably block that time off so that no other person can join. But if I'm really busy, I'll keep that time slot open, usually like the week before an exam or something when everybody wants help. So that's how that works. I haven't posted the office hours and stuff, but it'll get posted into here. I do also want to mention that there is a graduate TA who will lead help sessions. And that is already decided. These are the times. So I'll put those in that calendar, but the graduate TA, so I think apart from my office hours, the graduate TA would probably be the best option. ALEC, it's a hit or miss. Sometimes they're not really that good, apparently, especially when it comes to like a class that's a little bit higher, like differential equations. But the graduate TA is actually a current PhD student, so he should know of everything that we're covering. And those are in person only here. My office hours to be determined, I'll send out a poll, but those would be hybrid. So it would also be possible for you to join by Zoom, but the graduate TA can only do in person. So I think that covers, because I went through all the links up here. And of course, there's some that are not activated yet because they're not relevant yet. So the daily practice solutions will get activated once we first have our first daily practice, and then homework and test solutions. The grade calculator, I'll introduce that when it becomes more important, usually like after the first test or something like that. And that'll help you be able to figure out like what you need to get in the class to get a certain grade. Any questions about just the housekeeping business? Okay. So I'm just going to jump right in to the material. Let's see if I can.
I have a quick question.
Yeah.
What's the difference between the blank lecture PDF and the blank lecture daily practice?
It's just the difference is it's a PDF versus the blank lecture and daily practice will open this giant Google Doc here. It's just I just export pieces of this as a PDF. Well, this also has a daily practice in it, but okay. So let's share my. Okay. So let's first just introduce what is a differential equation. This is so big. So there's two words in it. It's differential and equation. So we all know what an equation is. Equation is something basically that has an equal sign in it. Differential just means that not only do we have an equation, there are terms in it that are derivatives. So if this dx over dt was just x, then it'd just be an algebraic equation. But because it's dx over dt, it's a differential equation. Your derivatives could actually be not just first order derivatives, but it could be second order derivatives like d squared x dt squared, or fourth order derivatives. As long as there's some kind of a derivative in your equation, it's a differential equation. And so it's just a relationship of one or more functions and their derivatives. And these functions usually represent some kind of physical quantity like electrical charge or concentration inside some kind of tank of some salt or something. It could mean population of a bacteria. And you might want to have some kind of, you might have some physical understanding of rates of change of that physical quantity with some other, with itself, with, its own, itself. So that means you might have a, relationship between rates of change and the actual thing. And so it's the study of differential equation is just trying to find and analyze these solutions and the properties of those solutions. So if you look at this first one right here, you see here dx over dt. This implies that our x right here is our unknown sort of solution that we're trying to find. And because we're taking the derivative with respect to t, the implication is that our x is some function of t. So this is our unknown solution that we're looking for. We're trying to find x of t such that it will satisfy this differential equation right here. And we usually say that, so I'll say it like this. So I'll just say this is x is equal to xt. And you might call this x as your dependent and your t as your independent variables. And the fact that this x of t, we're going to always think of x as a function of t, where t is just, it's just one variable. So, if you've taken Calc 3, then you might have like x as a function of more than one variable. Then you might have partial derivatives. You might have, instead of just dx over dt. In our class, we're just going to think of all of our x's as univariate, so not multivariate. So just a single function of a single variable. If you had multiple variables, then you might have partial derivatives, and those equations would be called partial differential equations. But we're just doing ordinary differential equations for our class. So the unknown function depends on only one variable, t. Now, the order of your differential equation is going to be the highest derivative that shows up in your equation. So if you look at your derivative terms, there are, in this one, there's two. There's a second derivative and a first derivative. So you really just look at the highest order derivative that you see. So this is a first order differential equation. This is a second order differential equation. And this is a fourth order differential equation. And so that's just a intro to what a differential equation is. Of course, it relates derivatives. So I'll just say that it relates derivatives. So these are derivatives with one or more functions. Okay, so let's look at a really, really simple differential equation. So this one is a first order because it has only dx over dt in it. So we know this is a first order. And in general, you might have a first order differential equation with some function of t and x on this side. So you might have, like, for instance, this right-hand side could be x squared plus 2t, or it could be e to the t cosine of x, some function of x's and t's. And so you might have, depends on an independent variable and some solution x. And you have a first order, so it's going to be first order because you have first derivative. And this already has a lot of applications like growth and decay for populations, radioactive decay, thermal cooling, mixture, evaporation and flow. And so we'll go over all these types of applications, but this is a first order differential equation that's a really simple form. And you might, let's just see how a differential equation works. So again, we're keeping in mind that x is a function of t. So I'll just, all I did here was rewrote this same thing up here, but wrote that x is a function of t. So this is just making it very explicit that x is a function of t. And what does it mean to be a solution to the differential equation? So before we even try to solve the differential equation, why don't we just understand what it means to be a solution to the differential equation? So the first problem here just says verify that this function is actually a solution to this differential equations. So what we're going to do is we're going to say, we're thinking that this is actually, I'm giving you the solution. And then we're just going to say, is this actually satisfied? Does this actually satisfy this differential equation? So what I'm going to do to verify that is we're just going to take the derivative of this. So we'll just say dx over dt. You have the chain rule, so the 3 comes out and then multiplies with the 2, so it becomes 6e to the 3t. Derivative of 1 is 0. And so what I'm going to do is if you plug in this solution into this differential equation, you'll get 6e to the 3t is equal to 3 times, of course, we're just plugging in this into this x right here. And we're plugging in this here. And so we'll have 3 times 2e to the 3t minus, wait, no, it's going to be 3 times 2e to the 3t plus 1 minus 3. And then you'll have 6e to the 3t. This you can distribute, 6e to the 3t plus 3 minus 3. Of course, these go away. And so you have a true statement. This is what it means to satisfy a differential equation, is that if you successfully found the right solution, you should be able to plug it into the differential equation and it should actually give you a true statement. It should satisfy the differential equation, right? This is the same as in algebra. If you had an algebraic equation, you solve for x. You can plug that x back into your equation and you should make sure that it satisfies it. The only difference now is that you have a derivative showing up in your equation. Now, the point of our class is not to just plug in a solution. The point of our class is to actually find this. So if I gave you this, the game we're going to play is I give you this blue box, you find this red, so you got to be able to find. But every solution you do find, you should be able to plug it into, if you did it correctly, you should be able to plug it into this blue box, this original equation and get a true statement. So that's what it means to be able to be a solution of a differential equation, is that you found something, successfully found some expression for your solution that if you plugged into your differential equation, give you a true statement. But the goal is to try to find, I give you this blue and then you want to find this red. So let's do that. But before we do it for the most general case, let's look at a very simple case where you have a first order differential equation, dx over dt equals some function. I said before that function could be a function of both x and t, but let's make our life easier and just say it's just a function of t. So I'll just say just t, no x yet. Okay. This is actually so easy because you can just do anti-differentiation. You've seen this in Calc 1, so this is like the easiest kind of differential equation you could solve. Dx over dt equals t squared. Can you tell me what x must have been to be able to satisfy this differential equation? Again, x is a function of t, and all you're doing is taking the antiderivative of this, so it's going to be t cubed over 3. Right? That would be the antiderivative, but you also have a plus c. And it's really just the same as just taking the antiderivative of this right here. And we can see that this right here is going to be the expression for x that would satisfy this differential equation. And you can even, yeah, so you could even check this, but it's really not necessary. I mean, you could just say the derivative of this is equal to t squared. So that checks. So this is a general solution. General meaning that there's an arbitrary constant plus c that's coming from the integration constant. This c could be anything. It could be 1, it could be pi, it could be -7. Whatever this is, this x solution would still satisfy this differential equation because the derivative of a constant goes away. But you've probably also seen this. So the general solution has the arbitrary constant still in it. But what if there's an initial condition given to you? That will allow you to find what that c must have been. So for instance, if you had dx over dt equals sine of 3t, you can find the general solution. The general solution is just taking the antiderivative of this. So I'll just say, and the antiderivative is actually this. You could do the substitution method, but this also you can see pretty easily that the antiderivative sign is negative cosine of 3t. And you want to have the 1/3 because of the chain rule. You want to compensate for the chain rule. So this will be the general solution. The general solution still has the plus c in it. But then if they give you an initial condition, you've probably seen something like this before. So this is the initial condition. Then this is just saying that you need to make sure that whatever solution you have satisfies this condition, which means that when t is equal to, we have x is equal to 1. So of course, our general solution, I'll just write it out, is equal to -1/3 cosine of 3t plus c. And this initial condition is saying that whenever x is equal to 1, whenever t is equal to 0, x is equal to 1. So this is just 1 is equal to -1/3 cosine of 3 times 0 is just 0 plus c. This is 1 is equal to -1/3. Cosine of 0 is just 1. And so it's just this. And then this just means that c is equal to 4/3. And that's going to go in here. So our particular, I think the language you've probably heard for this is the particular solution is going to equal this general solution, but with the c being 4/3. I'll just say the general solution is the green underlying thing. Our particular solution is the red. So that's probably a review for most of you. Let's do a little bit more. So part A for this just asks you to find the general solution to this differential equation. You want to just find the antiderivative because this is just a function of t on this side. So you can just take the antiderivative, which is going to be like taking the antiderivative of this. You can do u sub if you want for this. So u is equal to t squared. Then you get that du is equal to 2t dt, which implies that it's half of du is equal to t dt. And you see the t dt here. So this ends up becoming 1/2 integral of d e to the e to the u du, and this is just the antiderivative of e to the u, it's just itself plus c. And then you can just plug in your u is equal to t squared. This is your general solution. So if your right-hand side is just a function of t, it's just taking the antiderivative. Now, the only change I made from part A to part B is that I took the t that's in front here and deleted it. But that actually has a big effect because now you can't really do a substitution, because if you did the substitution, u is equal to t squared, du is equal to 2t dt, you don't see a t. So you can't really find a substitution that works. So it turns out that this function e to the t squared doesn't have an explicit antiderivative. But there is this theorem that says that if you have dx over some derivative equal to some function, you can always write its antiderivative. So there's like two fundamental theorems. There's like one for computing the area under a graph, and there's one called the constructive theorem for antiderivatives. And so if you have this as your derivative equal to f of t, you could write your x, your antiderivative, as a definite integral. So for this problem, you'll see here that there's a pattern, right? So there's an f of t here, and there's an f of s here. So all you're doing is, if you can't find an explicit antiderivative, then you're just going to say a to the t. F of t becomes f of s, so it's going to be, of course, this is your f of t here. So I'm just going to write that in here. It's going to be e to the s squared and ds plus c. So that's, and this a can be anything. You could choose it to be 0 or 1 or whatever. It has to just be something that's in the domain of your integrand. So e to the s squared is defined for all real numbers. So that means you can set a to be anything. The other thing you need to, so this is your general solution, but because it still has the c in there, but you have this initial condition. So this initial condition is saying that whenever, so I'll just say x is equal to 3 when t is equal to 0. So if I plugged in this initial condition, it just says that x is equal to 3 whenever t is equal to 0. So it's going to be 3 is equal to the integral from 0 to a to 0 of es squared ds plus c. And you're trying to solve, right, whenever you have an initial condition, you're trying to solve for the c by plugging in the initial condition. But in this one, there's one thing that we didn't do yet, was decide on what a we want to use. So you can choose whatever a you want for this lower bound. But there is an a that would actually make our life the easiest for trying to find c. Do you guys have does anybody have an idea for what a would be to make this really nice? So for instance, what do you want this a to be? Or you're free to choose it to be whatever you want, as long as it's within the domain of e to the s squared, which is any number. Yes.
Would it be -1?
-1? You could, yeah, you could do that, but there's an easier thing. You plug it, make a equal something, you can get rid of this entire term entirely. This integral entirely. Yeah. Yeah. So if you make, so we're going to choose a to be 0. So if we choose this to equal 0, okay, so if we ended up choosing that to be 0, then this will end up being 0 right here. And the integral from 0 to 0 is nothing. So c will end up equaling 3. And so we end up getting that our solution to this initial value problem is going to be the integral from 0 to t, right? So it's this right here, e to the s squared ds plus 3. So this is Calc 1. Like if you remember, like you can write your antiderivative as a definite integral from a to t, where a could be 0 or 1 or any number, so long as it's in the domain of your integrand. This is not a super big deal, but like I did change the variable from e to the t squared to e to the s squared. That's because the book does it as well. The book actually puts a t bar. It's because there's a t in the upper bound here, they want to use a different variable for the integration. It's a dummy integration variable though, because it disappears in the process of taking the integral. So if you think about like if you were to actually explicitly take the antiderivative of this, you'll get some antiderivative with respect to s, and then you'll plug in your upper bound t, and then you'll plug in your lower bound a would be some number, and so your s disappears from your expression. So it really will end up being a function of just t in the end. It's generally people like to use a different letter for the integration here. So this f of t became an f of s here. And then we're free to choose what a is. And if you choose a to be 0 in this case, then you can get c to equal 3. If you chose a is equal to 1, then c would equal 3 minus the integral from 1 to 0. And that's like a complicated expression. So you'd rather choose a to equal 0. So then you get a really nice, easy expression for c. This process will always work, but there is, if you wanted to memorize, there's a formula for this. If you have a differential equation, dx over dt equals f of t, and some initial condition, then your if in the event that you can't find an explicit antiderivative and you want to leave it as a definite integral, then your t of 0 shows up here, and your x of 0 shows up here, and your f of t goes here. And this is consistent with what we had up here, for instance. So we had c is equal. So in our problem up here, t naught was 0, right? T naught was 0, and that showed up here. And our x naught was 3, that showed up here. And then our actual expression for our function was e to the t squared, and that showed up here as e to the s squared. And so you could, this formula will always work in general. And why would we want to do this? Okay, sometimes it's impossible to find an antiderivative, explicit antiderivative. Like if you try to actually compute the antiderivative e to the t squared, you wouldn't be able to. Sometimes it's really difficult to do it. Sometimes you might not actually have a mathematical function for your function. It might be like a bunch of data that you're trying to. So let's say you have like a rocket and you have like an accelerometer on your rocket that like just like records how your acceleration is as a function of time, and it could just be this weird jagged looking function. And so there isn't like a clean, like, oh, nice polynomial that describes that. You can still try to find the so-called velocity function or the position function by taking the antiderivative of something that's based off of just data, but you'd have to do like some kind of numerical integration. And so that's some application for when you might want to, when a definite integral is necessary or useful, or the only way basically that you can understand the problem. Okay, so we don't have time anymore, but the next problem is gonna have a right-hand side that is a blend of both t's and x's. So you can't just take the antiderivative with respect to t for this, because there's already an x on the right-hand side, and the x is also a function of t, and you can't really take the antiderivative of that without knowing what that x is. So we'll do that next time. So yeah, I'll see you guys on Friday. Even though I don't have office hours this week, if you wanted to meet with me, you can set up an appointment. But I'll send out a poll so people can select their preferred times, and we'll have office hours starting next week. But I'm still glad to meet with you if you wanted to meet this week.
Thank you, Professor.
Yes,
I always say Professor Yamamoto, but I nice to Ken, so.
it's okay either way, but I just wanted to let you know that you're free to